Hi, this is Gangadhar, lecturer in mathematics from Giraj Government College, Nizamabad, State Telangana. So today's YouTube topic is BSc second year mathematics subsequences. So now definition of subsequence. So first sequence definition. Sequence is a function from natural numbers to real numbers. Sequence is a function from natural numbers to real numbers is called a sequence. It is denoted by flower bracket Sn or open bracket Sn. So now definition of subsequence. Suppose Sn is a sequence. A subsequence of this sequence is a sequence of the form Tk for all k belongs to n, and for each k there is a positive integer nk such that n1 less than n2 less than so on less than nk less than nk plus 1 less than so on. So and tk equal to we write snk, tk equal to we write snk. So suppose Sn is a sequence and a subsequence of this sequence is a sequence of the form Tk form. So Tk form and Tk elements, how Tk elements are means, so S1, Sn1, Sn2, Snk, Snk plus 1, so on form. So now thus Tk is just a selection of some of the essence taken in order. So Tn means in the sequence Sn terms, in those terms we will take some terms. So those terms form one sequence. That sequence is called a subsequence of given sequence. So suppose sequence Sn terms are S1, S2, S3, S4, so on. Sn minus 2, Sn minus 1, Sn, so on. So in the sequence we have odd terms and even terms. In the sequence we have odd terms and even terms. Suppose we form one even term sequence. Even term sequence. Say S2n. So sequence terms are S2, S4, S6, so on, Sn minus 2, so on. So this sequence will say that S2n. And suppose we will take odd terms. So S1, S3, S5, so on, Sn minus 1. So this sequence denoted by S2n minus 1. So in the sequence, so even and odd terms are there. So first we will define one sequence of even terms. Next we define one sequence of odd terms. These even and odd sequences are subsequences of the given sequence. Even and odd sequences are subsequences of the given sequence. So Sn is the given sequence, then its subsequences are S2n, S2n minus 1. So now one example. So Sn equal to minus 1 to the power n. Then sequence Sn minus 1 1 minus 1 1 minus 1 1, so on. So in this terms are minus 1 so on, and 1 1 1 are there. So we will take two subsequences here we define. So negative terms one subsequence and positive terms one subsequence. So minus 1 so on, and 1 1 1. So these two are subsequences of the given sequence. So next example, Sn equal to n square into minus 1 to the power n. Sn equal to n square into minus 1 to the power n. So terms of sequence are minus 1, 4, minus 9, 16, minus 25, 36, so on. So here positive terms and negative terms are there. So we will define positive terms one sequence and negative terms one sequence. So these two sequences are subsequences of given sequence. So terms for so -1, -9, -25, -49. So these are negative terms sequence. 4, 16, 36, 64. So it is positive terms subsequence of sequence Sn. And here we define Snk term. Snk term is, so Nk is 2k, 2 into k, Nk is 2 into k, then Snk equal to 4k square. Snk equal to 4k square. So next one example, Sn equal to sin n pi by 3. Sn equal to sin n pi by 3. Terms are root 3 by 2, comma root 3 by 2, comma 0, minus root 3 by 2, comma minus root 3 by 2, 0, so on. So here root 3 by 2 minus root 3 by 2, 0 terms are repeated terms. So we will define one subsequence like root 3 by 2, comma 0, root 3 by 2, comma 0, comma 0, root 3 by 2, comma root 3 by 2, so on. This way we define subsequences of the given sequence. So now one theorem is there. The theorem statement is, if the sequence Sn convergence, then every subsequence converges to the same limit. So means sequence Sn is converged to L, then its subsequence also converges to the limit L. So now proof of the theorem. So let Snk be a subsequence of sequence Sn, and Nk greater than or equal to k for all k. So this is to prove by induction. So in fact n1 greater than or equal to 1 and nk minus 1 greater than or equal to k minus 1 implies nk greater than nk minus 1, which is greater than or equal to k minus 1, and hence nk greater than or equal to k. Next we will take let s equal to limit of Sn, and we apply limit here. So let epsilon greater than 0, there exists capital N such that n greater than n implies mod Sn minus s less than epsilon. So here Sn plus we will take Snk. Then the definition, k greater than n implies nk greater than n, which implies mod Snk minus s less than epsilon for all nk greater than or equal to n, for all nk greater than or equal to n. So from this we say that limit of Snk is yes, limit of Snk is yes. So here we will take sequence limit, Sn limit is yes, and here we show that Snk limit also yes. So therefore we say that, so sequence is converge to L, converge to S, then its subsequence Snk also converges to S. So now Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. So in the sets also this theorem is there. There the definition is Bolzano-Weierstrass theorem definition in the sets. So every infinite bounded set has at least one limit point. So in the sets, Bolzano-Weierstrass theorem statement is, so every infinite bounded set has at least one limit point. It is the theorem statement in the sets. So now in the sequences, so this theorem statement, Bolzano-Weierstrass theorem statement in the sequences, a bounded sequence of real numbers has a convergent subsequence. A bounded sequence of real numbers has a convergent subsequence. So it is the statement of Bolzano-Weierstrass theorem. So now we will see the proof of the theorem. So proof of the theorem. So first let x to the power m be a bounded sequence in R to the power n. So first let x to the power m be a bounded sequence in R to the power n. So the sequence x1 to the power m of first component of the term. So x to the power m sequence first term we will take x1 to the power m. So the sequence x1 to the power m of first component of the term of sequence x to the power m. So we will take x to the power m is bounded sequence of real sequences. So which has convergent subsequence. So we know every bounded sequence has convergent subsequence. So now x to the power x1 power m subsequence is x1 to the power mk. So according to Bolzano-Weierstrass theorem in the real number system. So according to Bolzano-Weierstrass theorem in real number system is every infinite bounded set has at least one limit point. It is the Bolzano-Weierstrass theorem in real number system. So now let x to the power mk be the corresponding subsequence of sequence x to the power m. So then the sequence x2 power mk of second component of x to the power mk is also bounded sequence of real numbers. So this way we define x to the x1 power mk, x2 power mk, so on we define. So these all subsequences are convergent sequences and bounded also. So we again have two corresponding subsequences of x to the power mk. So and therefore x to the power m in which the sequence first second components both convergent. Continuing for n iterations, we end up with subsequence, we say that z to the power m. So last subsequence is z to the power m. So that sequence also convergent and bounded. So in which the sequences of first, second, so on, nth component all convergent, and therefore the subsequence z to the power m itself also convergent in the r to the power n. So therefore we say that every bounded sequence of real numbers has convergent subsequence. So now one definition. Subsequential limits. Let Sn be a sequence in real numbers. A subsequential limit is any real number or symbol plus infinity or minus infinity, that is the limit of some subsequence of sequence Sn. So limit of subsequence is called subsequential limit. Limit of subsequence is called limit of subsequence is called subsequential limits. So when a sequence has a limit s, then all subsequences have limit s, then s is the set of subsequential limits. S is the set of subsequential limits. So now one definition, let Sn be any sequence of real numbers and S be the set of subsequential limits of sequence Sn. So now limit supremum Sn equal to, we define limit supremum Sn equal to limit n tends to infinity supremum of Sn such that n greater than n, that equal to supremum s. So limit supremum Sn equal to limit n tends to infinity supremum of Sn such that n greater than n, that equal to supremum s. And limit infimum Sn equal to limit infimum Sn equal to limit n tends to infinity infimum of Sn such that n greater than n, that equal to infimum s. So we say that supremum s is called limit supremum Sn, infimum s is called limit infimum Sn, and these two are called subsequential limits of the sequence. So now problem. So first problem. So Sn equal to minus 1 to the power n. So then terms of sequence are minus 1 1 minus 1 1 minus 1 1, so on. So it is a bounded sequence because here supremum of Sn is 1 and infimum of Sn is -1. So here supremum and infimum are exist means it is a bounded sequence. So here -1 comma 1 r in the sequence -1 comma 1 r infinite terms repeated. So we say that these two are limiting points of the sequence. So these two are limiting points of the sequence. So here the sequence has two limiting points -1 comma 1. So we say that it is not convergent sequence, but here we want subsequential limits. So now we define limit to supremum Sn. So limit supremum Sn equal to definition is supremum Sn. So supremum Sn value is 1. So limit infimum Sn equal to definition is infimum Sn and its value is -1. So this way we define limit supremum and limit infimum. So in the second problem, consider the sequence Sn equal to n square into -1 to the power n. The subsequence of even terms diverges to so first here Sn equal to n square into -1 to the power n means we define the sequence. What is the sequence here? Sequence Sn equal to first term is -1, second term is 4, next third term is -9, fourth term is 16. So this way we define the terms of sequence. Positive and negative terms are there. So negative values are tends to -infinity and positive values are tends to +infinity. Means terms of sequence lies between -infinity and +infinity. So -infinity is the least term. So we say that limit infimum s equal to -infinity and +infinity is the highest term. So limit supremum Sn equal to supremum Sn that equal to +infinity. So this way we define limit supremum and limit infimum. So in the next problem, an equal to sin n pi by 3. So we define the sequence s equal to -1/2 terms √3 by 2 comma 0 comma √3 by 2. This way we define the terms in the sequence, and so these three terms are repeated in the sequence. So here we have three limiting points of the sequence, and here we want limit supremum and limit infimum value. So highest term in the sequence is the √3 by 2. So it is supremum s. So this value is we say that limit supremum an. So in the sequence least term is -√3 by 2. In the sequence least term is -√3 by 2. So it is limit infimum and also infimum Sn also. So now the next problem. So an equal to 3 plus 2 into -1 to the power n for n belongs to n. So first list the first 8 terms of the sequence. Give subsequence that is constant. Take a single value. So sigma definition also write here. So here first in the sequence we write 8 terms. So first n equal to 1. So n equal to 1 plus 3 minus 2 1. N equal to 2, 3 plus 2 5. N equal to 3, 3 minus 1 1. 3 plus 2 5. This way we get the terms. We write up to 8 terms. So 1 5 1 5 1 5 1 5. So here we have only 2 terms. So we define subsequences two ways. So one is 1 1 1 1. So here 1 is constant. So next second subsequence is 5 5 5 5. So 5 also constant. So these two are constant subsequences of the given sequence 1 1 1 1 or 5 5 5. So your sigma k term is 2k minus 1. So now one more problem. So consider the sequences defined as follows: in equal to -1 to the power n, bn equal to 1 by n, cn equal to n square, dn equal to 6n plus 4 by 7n minus 3. So now the problem: for each sequence give an example of monotone subsequence. First we write monotone subsequence. Second, each subsequence give its set of subsequential limits. So subsequential limits means limit of the sequence. So now next find limit supremum and limit infimum. So which sequences converges or diverges? So which of the sequence is bounded? So here first we write sequence, next subsequence, so sequential limit, subsequential limits, next converge or diverge, next bounded, here we want. So now solution of the problem. First an equal to -1 to the power n. Sequence terms are -1 1, -1 1, so on. So here we have two types of terms, negative and positive, -1 -1, so on, 1 1 1, so on. So negative terms form one subsequence and positive terms form one subsequence. So we will take any one subsequence, 1 1 1, so on. Here we will take. So the sequence contains supremum and infimum values. So supremum is +1 and infimum is -1. So these two values also called limit supremum and limit infimum. So if supremum and infimum exist, then we say that sequence is convergent. Bounded sequence. So here we have two limits are there. Here we have two limits are there. So 1 comma -1 are repeated infinite terms in the sequence. So these two are limits of the sequence. So we say that these two values are subsequential limits. So here the sequence has two limiting points. So we say that it is not convergent, means it is divergent. Next problem, bn equal to 1 by n and sequence terms are so 1, 1 by 2, 1 by 3, so on. So in this we define even terms and odd terms. So we will take either even terms or odd terms or subsequences. So here we will take odd terms 1, 1 by 3, 1 by 5, so on are. So limit n tends to infinity, bn value we want, limit of the sequence we want. Limit n tends to infinity, 1 by n equals 0. So limit n tends to infinity, 1 by n equals 0. So in the sequence, terms start from 1, 1, 1 by 1, 1 by 2, 1 by 3, so on. These values are, sequence terms are decreasing. So decreasing up to 0, decreasing up to 0, as n tends to infinity implies 1 by n tends to 0. So now the sequence terms are lies between 0 and 1. The sequence terms are lies between 0 and 1. So therefore we say that sequence is bounded. What is the limit here? 0 is the limit of the sequence. It is called subsequential limit, and sequence converges to 0. Next problem, Cn equal to n square. Cn equal to n square. So sequence terms are 1, 4, 9, 16, so on. So here also even terms are there and odd terms are there. So these two terms, even terms and odd terms, form subsequences of given sequence. So we will take even terms here. So 4, 16, 36. So it is subsequence of given sequence. So next we find limit of the sequence. So limit of the sequence is infinity. Limit of the sequence is infinity. So now the terms of sequence are 1, 4, 9, 16 means the values are increasing. So these values are increasing up to infinity, because n tends to infinity, then n square tends to infinity also. So now sequence terms are lies between 1 to infinity. Sequence terms are lies between 1 to infinity. So here least value is 1 and highest value is infinity. So infimum value 1 and supremum value 0. Infinity. So infimum value 1 and supremum value infinity. So these two are called sequential limits. So now here we have only infimum means lower bound. Here we have only lower bound. So we say that sequence is bounded below. So sequence is bounded below. So here supremum does not exist means limit value does not exist. So sequence is not convergent. Sequence is not convergent means it is divergent sequence. So now next problem. 6n plus 4 by 6n plus 4 by 7n minus 3. 6n plus 4 by 7n minus 3. So sequence terms are 10 by 4, 16 by 13, so on. So here we will take subsequences either odd terms or even terms. So now limit of sequence is 6 by 7. So sequence terms are start from 5 by 2 so on up to n tends to infinity. Last term is 6 by 7. So sequence lies between the terms 5 by 2 and 6 by 7. In these two, 5 by 2 is the maximum value, 6 by 7 is the minimum value. So supremum of the sequence 5 by 2 and infimum of the sequence is 6 by 7. So the sequence has both supremum and infimum. So we say that it is bounded sequence. So therefore the sequence is converge to its limit value. So limit value is 5 by 2. So here one more problem. So let Sn and Tn be the sequences and their terms are 0, 1, 2, 1, 0, 1, 2, 1, 0, so on. This is a defined sequence Sn and sequence Tn terms 2, 1, 1, 0, 2, 1, 1, so on. So find limit infimum Sn plus limit infimum Tn. So limit infimum Sn plus Tn, limit infimum Sn plus limit supremum Tn, limit supremum Sn plus Tn, limit supremum Sn plus limit supremum Tn, limit infimum Sn Tn, limit supremum Sn Tm. First Sn sequence is given and Tn sequence also given. So we find limit infimum Sn and limit infimum Tn. So now the given set, first set values are 0, 1, 2, so on. Second set values also 0, 1, 2, so on. So in the set S, least value 0 and highest value 2. In the set T also least value 0, highest value 2. So limit infimum Sn equal to supremum S equal to 0. So limit Tn equal to supremum T equal to 0. So limit infimum Tn. Infimum Tn means Tn infimum is 0. So that equal to, we say that definition supremum T, that value is 0. So now limit infimum Sn plus limit infimum Tn equal to, both the values are zeros. So next limit infimum Sn plus Tn. So first here we find Sn plus Tn and in that, so we find infimum value. So Sn plus Tn value we write 2, 2, 3, so on. So here the terms 1, 2, 3 only, 1, 2, 3 only. In this least value is infimum u. So it is the 1. In this least value is infimum u. So it is 1. So limit infimum Sn plus Tn equal to 1. So next, limit infimum Sn plus limit supremum Tn. So limit infimum Sn is say infimum S limit supremum Tn we say supremum T. So infimum S is 0 and supremum T is 2. Supremum T is 2. So 0 plus 2 equal to 2. Next, limit supremum Sn plus Tn equal to supremum U, that equal to 3. So we know Sn plus Tn terms 1, 2, 3. In that highest value is 3. So limit supremum Sn plus Tn equal to 3. Next, limit supremum Sn plus limit supremum Tn equal to supremum S plus supremum T. Supremum S is 2. Supremum T is also 2. 2 plus 2, 4. So in this last problem, so limit infimum Sn Tn we want. Limit infimum Sn Tn we want. So we define Sn into Tn sequence. Sn into Tn sequence. We get 0, 1, 2. 0, 1, 2. So terms of sequence 0, 1, 2. In this we want infimum means least value. So limit infimum Sn Tn equal to 0. So limit supremum Sn Tn is 2. So limit supremum Sn Tn equal to 2. So here we have one corollary. Suppose the sequence An is sequence of positive real numbers converging to L, then sequence geometric means so limit of a1 a2 so on an power whole power 1 by n, limit is L. So now some theorems on limits, Cauchy's theorems. So first Cauchy's first theorem on limits. Cauchy's first theorem on limits. So what is the statement of this theorem? If an be a sequence of positive terms and limit n tends to infinity an equal to k, limit n tends to infinity an equal to k, then limit n tends to infinity 1 by n into a1 plus a2 plus so on plus an equal to k. So here if I want to limit n tends to infinity 1 by n into a1 plus a2 plus so on plus an, then we find the limit n tends to infinity n equal to k, then we write this total limit value also k. So now proof of the theorem. So we will take one example here. So limit n tends to infinity 1 by n into 1 plus 1 by 3 plus 1 by 5 so on plus 1 by 2 n minus 1. So here it is the form a1 plus a2 plus so on plus an by n form. So what is an value? An is 1 by 2 n minus 1. So an is 1 by 2 n minus 1. So we find the limit of this one. So limit n tends to infinity 1 by 2 n minus 1, limit is 0. So therefore we say that by Cauchy's first theorem on limits, so limit n tends to infinity 1 by n into 1 plus 1 by 3 plus so on plus 1 by 2n minus 1 equal to 0. So now one more problem. So here the problem. So limit n tends to infinity 1 by n plus 1 whole square plus 1 by n plus 2 whole square so on plus 1 by 2n whole square. So here we apply Cauchy's first theorem on limits. So theorem statement is the form a1 plus a2 plus so on plus an by n form. So here a1 plus a2 plus so on plus an is there. So denominator n is not there. So in the denominator n is not there. So divide and multiply with n. So here divide and multiply with n. So then the limit is the form 1 by n into 1 by n into 1 by n by something, n by here n square common. So that one also 1 by n into 1 plus 1 by n whole square plus 1 by n into 1 plus 2 by n whole square. So on this way we define. So in the sequence last term 1 by 4n. So we find a limit of 1 by 4n and limit n tends to infinity 1 by 4n is 0. So therefore we say that by Cauchy's first theorem total sequence limit is 0. So here next problem. So the same way we find the limit of third one also, we get 0. 1 by n 1 by n into n by 2n square. N by 2n square means 1 by 2n whole square, 4n square. N by 4n square means 1 by 4n, limit 0. So total sequence limit also 0. Third problem. So now in the fourth, so same model. So limit n tends to infinity 1 by root n plus 1 by root n plus 1 plus so on plus 1 by root 2n. So here also denominator, in the denominator n is not there. So divide and multiply with n. So then 1 by n into n by root n plus so on plus n by root 2n. So here we find limit of n by root 2n. n cancel 1 by root 2. So we get the limit value n by root 2n. n by root 2n means root n by 2. Root n by 2 means its limit value is infinity. So by Cauchy's theorem total sequence limit is infinity. So now proof of Cauchy's theorem. So statement: suppose an is sequence of real numbers such that an tends to L as n tends to infinity, then the sequence of arithmetic means 1 by n into a1 a2 so on an also converges to L. So limit an equal to L, then limit a1 plus a2 plus so on plus an by n limit also L. So now first sequence an converges and it is bounded. Sequence an is converges and it is bounded. So we say that converges to L. Sequence an is converges to L, and we know every convergence sequence is bounded. So here we apply convergence definition. So there exists m greater than 0 such that mod an less than or equal to capital M. It is the definition of bounded definition. So sequence an is bounded means there exists m greater than 0 such that mod an less than or equal to capital M for all n belongs to n. So now we apply definition of convergence. Let epsilon greater than 0, then there exists n1 belongs to n such that mod n minus l less than epsilon by 2. So boundedness definition, mod n less than or equal to capital M. So convergence definition, mod n minus l less than epsilon by 2. So now we now set up the stage estimate. So the value. So we want a1 plus a2 plus 1 plus an by n equal to L. We show that limit value. So here we apply mod a1 plus a2 plus 1 plus an by n minus L. If that value less than epsilon, then we say that sequence limit is L. So minus L, which is less than or equal to, we write 1 by n into, so a1 minus mod a1 minus L plus mod a2 minus L plus 1 plus mod an minus L. So assuming n greater than n1, so this inequality is splitting. So then we get epsilon by 2 plus epsilon by 2 plus 1 plus epsilon by 2. So n times epsilon by 2 addition is n epsilon by 2. So this way we show that a1 plus a2 plus 1 plus an by n minus L less than epsilon by 2, which is less than epsilon. So we say that total sequence limit is L. So now Cauchy's second theorem on limits. Cauchy's second theorem on limits. So if sequence an is sequence of positive terms and limit n tends to infinity, an plus 1 by an equal to k, then limit n tends to infinity, an whole power 1 by n value k. So limit n tends to infinity, an plus 1 by an equal to k, then limit n tends to infinity, an power an whole power 1 by n value also k. So here we will see one example. So show that limit n tends to infinity, n power 1 by n equal to 1. So now an equal to n and we want an plus 1, n plus 1. We find the limit of an plus 1 by an. N plus 1 by n means we write 1 plus 1 by n. We apply both side limit. So 1 plus 0 equal to 1. So we get limit n tends to infinity, an plus 1 by an equal to 1. So then Cauchy's second theorem, limit n tends to infinity, an power 1 by n limit also 1. So therefore limit n tends to infinity, n power 1 by n value also 1. So here one more example. So prove that limit n tends to infinity, n factorial to the power 1 by n equal to e. So here we write n factorial to the power 1 by n equal to whole power 1 by n is common, n factorial by n power n whole power 1 by n. So here it is the form bn to the power 1 by n. We say that bn equal to n factorial by n to the power n. So we find the limit value bn plus 1 by bn. So that equal to 1 plus 1 by n whole power minus n, means 1 by 1 plus 1 by n whole power n. So n tends to infinity, then its limit is 1 by e. So limit n tends to infinity, 1 plus 1 by n whole power n limit is e. So here we get the limit is 1 by e. So therefore total limit value sequence limit is 1 by e. So now thank you.